Great. Hello, everybody. My name is Timur. I want to talk to you today about a new feature that is being proposed for C++ 26. So it's not actually yet in the standard, and it's not even yet in the C++ 26 working draft. But I think we will get there. We have enough time. C++ 26 feature freeze is next year. We have a pretty good proposal, so I think it's probably a good chance it's going to get in. So it's this paper here. This is the paper. The feature is called contracts. And I'm going to mention a bunch of these committee standardization papers today. They all have these paper numbers, like this is P2900, R10 is the revision number. And if you see any of those numbers, you can go to w21.link/paper number, and that's going to give you the latest revision of that paper. So there's going to be lots of paper, like P numbers all over the place, and that's where you can find them and look them up. So this is P2900 R10. This is something I've been working on for a few years now, together with a bunch of other people. And yeah, this is something we are proposing for C++ 26. And the proposal has been quite stable for a while now in terms of the major kind of design. So I think even though it's not yet in the standard or even in the C++ 26 working draft, it's a good time to talk about it. So we all know what this is about. This paper is a culmination of over 20 years of trying to get this feature in the standard. The first contracts proposal was actually submitted in March 2004. So that was over 20 years ago. So that was designed after the way it worked in D, which was released in 2001. That proposal didn't work out. There was then a second proposal, which was motivated by the Bloomberg BDE library and the assertion markers they have there. That proposal also didn't succeed in the committee. Then there was a third one, which some of you might have seen, might have been familiar with. It's this double square bracket version, which almost got into C++ 20, and then very dramatically got pulled out. And now we're kind of getting towards the end of the fourth cycle of this. It's like this thing. I don't know if anybody of you has watched Battlestar Galactica. It all happened before, and it will all happen again. It's kind of this kind of thing. We're on the fourth cycle now. But we still have some time before the C++ 26 feature freeze. So I hope that this time we're going to actually make it. I think it's looking a lot better than in these previous iterations. So why has it taken us 20 years to come up with a proposal that looks decent? Well, that is linked to the question, what are contracts? So the concept of contract itself is actually a lot older than even this first proposal from 20 years ago. In fact, the concept of design by contract has been introduced by Bernd and Meyer back in 1986. So that's almost 4 decades ago. And it's an approach for software design which he developed together with his language Eiffel, which was released around that time as well. And the idea is to define formal, precise, and verifiable interface specifications for software components, extending the ordinary definition with preconditions, postconditions, and invariants. And those are called contracts in accordance with the conceptual metaphor with business contracts. Like you have obligations, and then you have rights, right? So it's kind of this two-way contract kind of thing between a component and another component using that component. So invariants are really interesting, but it turns out to specify them correctly for C++ is really, really hard. So we are not done with that yet. So invariants are unfortunately not part of this first iteration, version of this proposal. So we are going to extend it in future standards, hopefully. But this paper does not have invariants in it yet. So we expect that to be added as a future extension. So we're going to primarily be talking about preconditions and postconditions. So the concept of preconditions and postconditions is basically a contract between a function and its caller. And a precondition is conditioned on either the arguments you pass into the function or some other state of the program that is observable when the function is called. And it is on the caller of the function to satisfy that part of the contract. And the postcondition is kind of the flip side. It's either the value that the function returns or some other state that the function sets up or some other observable behavior that the function has. And the contract is that when the function returns, those conditions will be satisfied, and that is on the implementation of the function to satisfy that part of the contract. So preconditions, postconditions. And those contracts actually exist in C++ today, right? So that's not a new thing at all. That's a concept that we have today. And most frequently, contracts are specified today in the form of so-called plain language contracts. So they're specified in human language rather than in code. Most often it happens in code comments. I'm sure many of you have these code bases where you have something like operator square bracket has a precondition, right? You cannot call it out of bounds, otherwise you have a bug. It's a precondition violation. It's on the caller to call this function correctly. And typically, we document this plain language contract in the form of a comment in the code, or sometimes in a separate document. For example, the C++ standard actually specifies preconditions and postconditions for all the functions in the standard library. So that's just in the standard document. It says preconditions pose smaller than size for this particular function here. Standard also goes on to specify what preconditions and postconditions are. That's actually interesting. Like, you can define this slightly differently, what happens when a precondition is violated, and we're going to talk about that later. And the standard says that the preconditions are the conditions that a function assumes to hold whenever it's called, and violation of any preconditions results in undefined behavior. So that's probably not always the best way to deal with a precondition violation, but we're going to talk about that later. And postconditions are just the conditions established by the function. So that's all consistent with kind of the mental model that we have here. Sometimes contracts are also not actually written down anywhere. They're just assumed, or they're kind of implicit in the way developers think about their code. For example, in some code bases, it's a convention that if you have a const member function, then that will be thread safe, and you can call that from multiple threads simultaneously. But that's typically not written down. That's just something you know when you work with that code base. That's also a contract. Okay. So, but what you want to do here, that's kind of the novel bit, is we want to express contracts in C++ code rather than just in plain language. And we call that contract assertions. So that concept had quite a few names in the past, but this is the one we settled with, contract assertions. So that is what we're proposing. That's what this proposal is about. It adds this new syntax to let you write contract assertions. So you can, if you have a function declaration here, widget, get widget, takes a parameter, returns a value, you can now, to that declaration, add this new syntax pre, and then in parens a Boolean predicate, and post in parens a Boolean predicate. You can also have multiple pre and post. And this way express what the preconditions and postconditions of the function are in code. And there's a third type of contract assertion, which we call assertion statement, which is spelled contract assert. You would really like to spell it just assert, but unfortunately that conflicts with the existing macro. So we had to pick another keyword. Contract assert is basically the same thing, except that it's inside the function body and not on a declaration. So we have these three types of contract assertions. These two, we call them collectively function contract assertions, because you put them on the declaration of a function or a lambda. And the assertion statement is not a function contract assertion, because you put it inside the body or anywhere you can put a statement. And those three together are just contract assertions, and that is basically it. That is what you're proposing. Now, what are contracts for? And that is an interesting question, because if you ask 5 committee members, you're going to get 6 different answers. And that has been the case since certainly I have been working on this topic, and I'm sure for a long time before that as well. So after phase 3, kind of the third iteration, kind of went unsuccessfully, and contracts were ripped out of the C++20 working draft, we founded SG21, the contract study group on the committee, which I'm the co-chair of. And we said, OK, let's go back to the basics and figure this out. So we wrote this paper that tried to collect the different use cases for contracts. What could you use contracts for, or any kind of hypothetical feature that we could specify and implement for in C++. Guess how many use cases we found? Anybody wants to shout out a number? 10. Any more? 15. OK. 196. And the paper lists them all. So a lot of them are kind of very specific. That's why the number is so high. But you can kind of group them into buckets, and you end up with something like this. So there's a lot of stuff going on here, right? So there's, you see there's here safety and security. Then there's also some stuff about performance optimization. So they typically there's some tension between those things. Then people want to use them for correctness and formal proofs, tooling, documentation, runtime checks, all kinds of stuff, right? So that is a bit of a problem, because you can't really do all of these things at the same time with one feature. Otherwise, it's going to be so complicated that you'll never be able to specify and implement it. So there's kind of a bit of an analogy here. So as a Russian who grew up in Germany, I can draw on the rich folklore of both of those countries. So this is one thing from German folklore, which the Germans will be familiar with. It's the egg-laying wool milk pig. It's a thing that does everything. It gives you milk, it lays eggs, it gives you fur and meat and everything at the same time. Unfortunately, that thing doesn't exist. So for a long time, the problem was we were trying to specify a feature that does this, and then we found out that that's impossible. So then the next thing was, okay, we need to pick some subset of the use cases we support. We need to descope. And then we went and tried to do that and discovered another problem, which I'm going to illustrate with this picture from Russian folklore, the swan, the pike, and the crab. It's a very famous fable from the beginning of the 19th century. The idea here is that there was a cart with some food that these animals really want to have. So they want to get the cart home, but unfortunately they're all pulling in different directions. Like the swan is pulling up into the skies, the fish is pulling down into the river, and the crab is pulling sideways, and so they're all pulling different directions, and the cart is going nowhere, and it's still there where it was today. So this is a situation we were in for another few years. Everybody wanted to get their favorite use case first, and we didn't really make any progress there. And so that's also not a good way to specify a feature. And then we kind of realized that, okay, we need to do something else. We need to just agree on a first version of this, which will support some use cases but not others. And that is basically what we did with this paper. We are laying the foundation, and we are purposefully discarding some use cases, but we designed this feature in such a way that you can add them later as an extension. Okay, so we're not cutting anything off for the future. We're just saying, if you want this use case, you're going to support it today. If you want this other use case, okay, well, you're going to have to maybe wait until C++ 29 or C++ 32, but there's a path towards getting there, right? So we're not cutting off that design direction. And once we kind of decided that that's what we need to do, we started making really good progress. And now we have a complete and coherent and consistent paper. So the question is not really what contracts are for, because they're for all of these things, but what are P2900 contracts for? What is the MVP for that we are proposing for C++ 26? And this is the best kind of explanation that I came up with. It's a bit long. P2900 contracts allow the programmer to express expectations about program correctness at certain points in a C++ program, particularly, but not only, when calling and returning from functions. Optionally verify that those expectations are met in order to identify program defects, and then manage how identified defects should be mitigated in a portable and scalable fashion during program evaluation. So that is what this paper proposes we should be able to do. Okay, so we're going to go through, there's a lot going on here. We're going to go through this. We have some time left for that. So let's start. So this is kind of the core of it. P2900 contracts allow the programmer to express expectations about program correctness and optionally verify that those expectations are met. Okay, so really important here is this optionally verify bit. This is kind of, I think, the one thing that distinguishes this feature from everything else we have in the language today. So really important to recognize here is that contract assertions are redundant checks. In a correct program, you don't need them and they do nothing. Right? So they're only there and they're only really interesting if your program is incorrect, and they help you find out that your program is incorrect and do something about that. So I'm going to explain this with a metaphor that I borrowed from Lisa Lippincott's excellent talk, Perspectives on Contracts, from this year's CPPCon. Just a couple of months ago. I think it's a good way of explaining what we mean by redundant checks. So let's imagine you want to subtract two numbers with pen and paper. Okay. So we all know how to do this. We all learned an algorithm for how to do this in school. Depending on which country you went to school in, it's going to look slightly differently, but we know how to do this. It's going to look something like this, right? You can perform this computation on pen and paper. It's pretty quick if you're kind of used to doing it, and we get a result. So now, in most cases, you probably say, okay, well, great. I know what the answer is. I'm going to move on with my life. I'm going to use that answer in whatever the next thing is that I want to do. However, sometimes, if that answer was wrong, if you made a mistake, that would be really, really bad. That would have catastrophic consequences. Or for some other reason, it's something you really, really need to avoid in the current moment. So there's one thing you can do. You can actually double check that what you did was correct. You can basically take the last two numbers and add them up, and then see if you get the first number back out, right? And so if you do, then you know that your computation was correct. And if you don't, you know, oh, you made a mistake, there's a bug, right, in your algorithm. Somehow you didn't do the right thing. And so that is a very good way to find errors in your calculation, but it is redundant in the sense that if you didn't make a mistake, you're just wasting time. You're performing computations that are not actually useful. So this is not something you would want every school kid that does this in school to do every time, right? That would waste a lot of time for a lot of people. But if it's important that the result is correct, then you can optionally say, okay, I'm gonna do this extra step to kind of just be sure. And it sounds a little bit similar to unit tests, but it's not quite the same thing. So unit tests here on the left-hand side, you call a function with a concrete input, right? And you expect a concrete output. Whereas contract assertions, they're on the other side. They're on the function declaration, and they kick in no matter how you call the function, right? So it's a kind of a different way to go about it. It's a bit like a hand and a glove kind of thing. The other thing that contracts are not is they're not error handling. So it's really important that we're talking here about identifying program defects. And there's a difference between an error, like something didn't go the way you expected, or you got invalid input or something, so you need to recover and do something else, and a program defect, which is a bug. A bug is something that you can typically only mitigate or fix by actually changing the code that you wrote, right? So the code is wrong. So there's a difference between errors and program defects. So contracts are, in particular, not for input validation. If you, for example, here have a function that takes a string and parses it, right? And then if it takes an empty string, that would be an error. Then you shouldn't do this with a precondition assertion unless you're sure that the string definitely will not be empty, because you set up your program in such a way that that can never happen unless you have a bug right there. But if the string comes from a file or the network or some user thing that you don't have control over, then you don't want to do this, because this is a redundant check. It might be turned off, right? So what you want to do is and if you do it like this and the check is not performed, then you get UB here, which is bad. So what you want to do is you want to handle the error by throwing an exception or returning an optional or whatever. Like, there's many strategies for that. But error handling and contract checking are fundamentally very, very, very different things. So we talked about optionally verifying. So the checks can be on or off. Okay. So how can we do this today without contracts? There's different options, right? So if you have a function with a narrow contract, the function has a precondition. The classic example is operator square bracket. Then what can you do with this? Okay, so you can say, okay, we just do nothing. We just document the contract here. And then if the contract is not satisfied, well, you just get what you get, right? So you just return the data pointer here, and if you're out of bounds, well, then you get UB. All right, that's probably the fastest way to do this, but it's probably not very safe. You get UB here. So maybe you want to instead call a function with a wide interface where this is an error but not a precondition violation. So you want to handle the error. For example, instead of operator square bracket, use at, you throw an exception. Okay, then you don't have UB anymore. It's great, but it's not a good solution if you want to handle this as a bug. Like, what you can do instead is something that we learned about from Louis yesterday when he talked about library hardening. You can do this, right? You can say, okay, it's still a narrow interface, it's still a bug, it's still a precondition if you call it out of bounds, but we're not actually going to just ignore it. We're going to check it and then trap or terminate or whatever if the precondition is violated. The problem, though, is that it kind of depends on what you want to do, whether you want to do this or the other thing or the other thing. So what contracts let you do is they let you just express that there's a precondition there, right? But this syntactic thing does not guarantee any particular runtime behavior associated with it. So it could terminate, it could just ignore it. It depends on what you want to do. So it gives you this freedom to choose, depending on the use case, whether you want to perform the extra calculation to make sure you're right, or whether you want to just move on because you're pretty sure you're right. And if occasionally you're wrong, then that's fine in this case. So we said here that P2100 allows the programmer to express these expectations and do these things. So who is the programmer? And it turns out, actually, that there's quite a few people here. There is the caller of the function, the one that is responsible for setting up the preconditions and making sure they're met. There's the callee, that might be a completely different person in a completely different company, implementing the function, who must ensure that the postconditions hold. And then on the flip side, the caller can expect that the postcondition hold, and the callee can expect that the preconditions hold. But if you're talking about, what this code should actually do, there is actually a third person, which again could be somebody completely different in a completely different company, the person who's actually compiling the program, right? And that person gets to enable and configure these contract checks and decide what happens in case you have a violation. So this is kind of the setup. This is what you want to be able to do. Turns out there actually is already a feature in the C++ language that lets you do exactly this. Who knows what it is? What's the feature that lets you do this? Macros. Macros. Which one? Assert. Yes, you can do this. It gives you all of the properties that I just showed in the last slide, right? The library author can write it. The library user needs to make sure that this holds, and the person building the program can enable or disable ndebug and decide what happens with the check, whether the check happens and what happens when it fails. So we already have this in the language. This is already a contracts facility. Unfortunately, it's not quite enough. So, and then we get back to the question, what are P2100 contracts for? And here's another answer to this question. They provide a superior replacement for assert and other assertion macros. So this is really kind of the one-line raison d'etre for this feature. This is why we need this in the language, because macros aren't really a good solution. Here's an example. Macros don't know anything about modern C++ syntax. They don't know what curly braces or template brackets, and if you have a comma in between, it's going to think it's the next macro argument, and your parser is going to break. That's bad. Contract assertions, pre-post or contract assert, all three of them are core language features. It's proper C++. It's not preprocessor, so that's going to work. Another thing is, if you have an assert macro, you compile one translation unit with ndebug off and another translation unit with ndebug on, and then you link them together in the same program, you are not going to have a good time, because that's an ODR violation. With P2100, that is not a ODR violation, even though you can get very similar options here that we expect compilers to provide. But the language knows about this. It's not just textual replacement, right? So the compiler can make sure that this is going to have reasonable behavior. Another one is if you have a macro and it's disabled, it's just textually thrown away, right? So you can have any expression in there that doesn't compile. It's like some class that you deleted last week. And everything's great until you disable ndebug again, and then it just breaks. So it's prone to this bit rot problem. And again, here, this is C++ is not going to throw out the tokens. Even if the checks are disabled, it still needs to be a valid C++ expression. Otherwise, you get a compiler error. So you don't run into this problem either. And most importantly, you can't put assert macros on declarations, which means at the call side, you're not going to see that they're there. A static analysis tool is not going to see that they're there unless it can look into the definition. Your IDE is not going to see that they're there. It can't show you a nice bubble to see this is the contract of the function. And the user, the reader, cannot see that they're there by just looking at the header, right? So you really want these things to be on the declaration, and we allow that. And then on the implementation or any subsequent declarations, you can repeat them or not repeat them. This is optional, but they have to be on the first declaration of the function. Another cool thing that you cannot really do with macros is we allow you to refer directly to the return value of the function. And so this is this other piece of syntax here. You have post, and then you can put any name there, R, X, whatever you want, colon, and then an expression. Then you can use that name there, and it's going to refer to the object that the function returns. And this is kind of similar conceptually to structured bindings, where you define a structured binding, you have an object that doesn't have a name, but you give names to the parts of the object. This is similar here. This is an object that you can't normally name in C++ today, especially if you're returning a PR value, like an expression, right, instead of a named object. But this thing lets you actually name that object. Okay. And this also works with guaranteed copy elision if you have, so that's something you can definitely not really do with macros. If you have a function that returns a PR value of a type that's not copyable, not movable, yeah, there's nothing to name in a macro, right? But the P2100 will actually give you a way to refer to this guaranteed copy elision returned object here. So actually, this red here in post refers directly to the object in main that is being initialized here. And in order to understand this, we need to understand this bit here. So context assertions are evaluated at a particular point in the program, and in the paper we have a specification for this. You know, when exactly these things happen, and basically precondition is checked when the function is called. Postcondition is checked when the function returns. The assertion statement is just called when you execute that statement. So there's no surprises there, except that there's this one interesting property here that postcondition assertions are evaluated after the result object value has been initialized and after local variables in the function have been destroyed, but before the function parameters have been destroyed. So because it's evaluated after the result object value has been initialized, we can do this, and it will actually refer to the object in main that you have already initialized by the time post gets checked. And you can actually observe this via this cool trick. Don't do this at home. You can initialize a variable and then pass to the function the address of the variable that you are about to initialize. And then the function is going to get evaluated, it's going to return a value, and then A is going to be initialized with that value, and then post is going to be checked. And the address of that thing in post will be the address of A in main. So those addresses are guaranteed to compare equal, which is kind of weird and fun. There's a little exception for trivially copyable types, which can be passed in registers. Then things get a bit weird, but that's a different topic for a different day. So now we know how this works. So this lets you manage how identified defects should be mitigated. So this begs the question, what happens actually when a contract check fails? So for CAssert, you know, we know the answer, right? So if the checks are on and it's false, then it logs a message to standard output and terminates. So for P2100 contracts, something slightly different happens. It calls this magic function called the contract violation handler. But it turns out that there's a default contract violation handler, and what the default contract violation handler does is it logs a message to cout and terminates. So the default behavior is actually exactly the same as the one for the assert macro. However, the thing that you get here is you can customize that contract violation handler. And you can do something else instead of printing and terminating. And you can't do this with assert. You can do this with custom macros. And I think that's a big reason why people use custom macros. Who's using custom assertion macros in their code? Okay, quite a lot of people. So you want to do something else. So you can do this with macros, but you can't do this across your entire program and the entire ecosystem, right? Every library will have their own assertion macros. Every framework will have their own assertion macros. They will have their own handlers if you have any. What P2100 lets you do is it lets you have one handler for the entire program. So no matter where the assertion fired, what library from or whatever, it's all going to end up in the same global handler. And you specify this not at compile time, not at runtime, very good reasons why we can't do either thing, but at link time. And it works exactly like operator new and operator delete works today. You can just define your own definition and link it in. And then it's going to be replacing the one that the compiler provides. I think compilers call this a weak symbol, so this is pretty much exactly what this is. This is going to be implemented as a weak symbol. So what it lets you do is it lets you define a function as long as it has this exact name and this exact signature. It's going to replace the default correlation handler, and it's going to do whatever you want. You can do your own logging there. You can call home, do a network request to some server to say, hey, there was a contract violation handler violation in the customer's code. You could also set a breakpoint. That's pretty cool. We have that feature now as well, also in CSS 26. Or you could spin until the user attaches a debugger and then set a breakpoint. That's pretty cool things you can do. You can print a stack trace. You can print a stack trace and then fall back to the default contract violation handler, which is you can do with this quite long-named function that we provide here, which is going to just fall back to the default. And you can throw an exception. That is actually very interesting. because that lets you do something else when you have a contract violation and you know you can't continue into the function because that might have UB, that might crash your program, but you also can't terminate. And there are use cases where you really, really, really don't want to terminate, even if you know you have a bug. And so you can instead throw an exception, unwind the stack, and then at some point have an exception handler that says, okay, well, we're in red territory now. We know that there's a bug, like there's a weird state, but we can't terminate right now, so let's do something else. Lets you do that. Of course, if the function is no accept, then it's still going to terminate. So if you want to do this, you have to follow the so-called Lakos rule that if a function has preconditions, you can't put no accept on it, even if it never throws when you call it correctly. And this idea is not new. It's been around for decades. So the C++ standard has been following this rule. This is, for example, why vector operator square bracket doesn't have a no accept on it, even though it will never throw if you call it correctly. Because if you call it incorrectly, a valid strategy is to throw an exception, right? So this is something that some people might want to do. If you are using a library that has no accept all over the place, you probably don't want to do that. If your code doesn't know how to handle exceptions, you probably don't want to do that. That's fine. Then just don't do it. It's an option for people who need it. It's not something that everybody has to support. So there's a little bit of standard library API here. Everything is in namespace contracts. Everything's in header contracts as a small piece of API, and it's only needed to implement this violation handler. So you don't need to include this header or worry about this if you just want to write pre-post contract assert, only if you're going to implement this handler. And I suppose this is just going to be one person per company, so that is not going to be a very frequent thing to do. And this is all the library API. This is all we have. So the contract violation is called. You get this object passed in, and then it has these member functions here that lets you figure out what happened. Comment, it gives you like a string that tells you this is what happened. Then location gives you a source location of the contract violation, etc., etc., etc. There's like two member functions here that we added in the latest revision, which is not public yet, which is if the predicate didn't actually evaluate to false, but you got an exception while you were checking the contract, you get access to that exception here. That's really cool. And it's also going to tell you if the next thing after the handler has returned is going to be that the contract violation handling mechanism wants to terminate your program, so you can okay, the next thing that's going to happen is it's going to terminate the program, so you can do something else, like throwing an exception. Right. So we're already talking about how identified defects should be mitigated in a portable and scalable fashion, right? That is really important. So let's go back to this idea that we have these three different personas, and this person here is the one who enables and configures the contract checks and decides what happens in case there's a contract violation. So we already saw that you can install a contract violation handler, but we haven't really talked about how these checks are enabled and disabled. And so for assertion macros, there's two options, ndebug on, ndebug off. For P2100 contracts, you get a few more options. You, in fact, get 4 so-called evaluation semantics. There's the ignore semantic, which basically does nothing. It has no overhead, nothing's checked, no code is being run, no instructions are being emitted, except that the expression is still parsed and entities in it are still ODR used. And there's reasons why you need that. Then there's observe, which is going to check the predicate of the contract, so the Boolean expression that's inside the pre-post contract assert. And if that expression returns false or throws an exception, you got a contract violation, and it's going to call the handler, and when the handler returns, it's going to continue. So that's really good if you have a legacy code base that is running in production. You don't want to terminate that, but you want to insert new checks in there to see if you can find bugs. Then there's enforce, which is the same thing, but after the violation has returned, it terminates the program. So that's actually default. So default is the safe thing and the verbose thing. You have a contract violation, you're going to get all of this information about what happened, and then you're going to terminate to make sure that you don't continue past a contract violation and you don't execute some invalid state. So that's the safe option. And then the only problem with this is you're still going to call the handler, set up this contract violation object. So there's a bit of code bloat and overhead, and you also need to catch an exception. So sometimes you don't want to do that. Sometimes you want to make sure that your program terminates so it's safe, but you also want to do it as fast as possible and give the least possible attack surface to an attacker. So that's kind of a safety critical context perhaps, where if you know you called an operator square bracket out of bounds, you just want to insert like a trap instruction and just terminate as quickly as possible and not do any of the other stuff. And this is kind of the safest option, and we call this the quick enforce semantic. So this is pretty much exactly what Louis and Konstantin were talking about yesterday when they were talking about library hardening. This is exactly what this is. This is the quick enforce semantic. And then there's a fifth semantic, which we don't propose in this paper because this is one of those use cases that we decided not to cover in the MVP because it doesn't have to do with identifying defects, which is our focus here. But it kind of exists. It is the so-called assume semantic, where you don't check the predicate, but it's not like ignore. It is that you then assume that the predicate is true and you optimize the program based on that assumption. So it works like the assume double square bracket attribute that we have since CSS22, but it's actually integrated into the contract facility. So you can turn the assume into a check, and it's actually way better than the standalone attribute thing. But if you misuse it, you might inject undefined behavior in your code. So it was a little bit controversial in the committee when we discussed this, so we decided, okay, let's decouple this topic from the main proposal and get back to it later. So we're not proposing this semantic in this version of the paper, even though conceptually it exists and it's kind of part of the mental framework. So how do we choose the semantic? So there's 4 of them, right? Ignore, observe, enforce, quick enforce. So you can choose them at compile time. So we expect compilers to just give you a flag very similar to ndebug. But the paper doesn't actually say. It says the choice is implementation defined. So you could theoretically choose them at load time, at link time, or even at runtime. Like the compiler could insert hooks, and then you can trigger those hooks at runtime. Of course, that would then have overhead, so that all of these options have different trade-offs. But we want to enable all of these options. And there's a bunch of papers here that talk about the different use cases and why you want to enable all of these options. Some of these use cases are things like this. Well, you can say, OK, the semantic, whether it's checked or not, and what happens is the same in every translation unit. That's what we do with macros today. You can say, oh, check only pre but not post, or check only a random subset, or check only every 10th assertion, or other things like that. Or we can also allow elision if the compiler can prove, OK, we're checking the same thing twice. I already checked this. Let me remove the second one because I already know it's going to be true. There's a consequence of doing this, which is you can't really rely on side effects happening when you have a side effect in your assertion, which is, I would say, bad practice. Don't do this, but some people do this. Here's an example, paraphrased from the Clang code base, where like they have an assertion that you don't iterate more than n times. So when the assertion is on, it's going to keep some state here. It's going to keep a counter, and when that counter hits like whatever number, then the assertion fires. Of course, if you can't rely on the semantic being the same, whether it checks the thing or not, being always the same in this translation unit, or even every time you evaluate this assertion, then you can't really keep any state in it, right? So it doesn't really work with P2100. So first of all, we don't have something like ndebug that you can add a conditional like declaration only when checks are on. We don't really have that. There are reasons for that. We will probably add that in a later version. But the bigger issue here is that you can't keep state in a context assertion, because the first time around it might be checked, the second time around it might not be, because the evaluation semantic is like the compiler can do whatever, right? So you can't really do this. You have to kind of factor the increment out of the assert, and in the assert you need to have a side effect free expression if you don't want this assertion to break. Okay, so that means there's a bit of a trade-off here that you can't just textually replace assert with contract assert. But you get some benefits out of it. So this is this thing we call the contract spam directive, which is the kind of the fundamental design principle of this paper, which says that the presence or evaluation of a contract assertion in a program should not alter the semantics of that program, which means that if you have a program and you add an assertion to it, you shouldn't turn the program into a different program. That should just never happen. And in some cases, we enforce this statically, like adding a contract assertion cannot affect overload resolution. You can't sphere on whether it's there. It's not going to change the no acceptness of a function, right? Because all of these things are things you could branch on, and then you would land in a different branch if you enable the checks. We don't want to let you do that. And if you add a contract assertion and it's not checked, it shouldn't cause any extra code to run. For example, we made it ill-formed if a unchecked contract assertion or any contract assertion triggers an implicit capture, because that would trigger a copy, even if you don't do the check. So that's ill-formed. In some cases, it's the responsibility of the user, in particular if you are using predicates with side effects that somehow alter the state of the program or the result of subsequent contract assertions. So don't do that. We call this destructive predicates. The simple version of this rule is just, don't use predicates with side effects. But sometimes you can have side effects that don't actually change the state of your program. It kind of depends on what you're doing. So, for example, it might be valid to check a flag that is an atomic, or not an atomic, but has mutexes around it. So you might have to take a lock, check a predicate, and then release the lock, or make an allocation to perform an algorithm that something is sorted in a particular way or whatever. So we don't really keep you from doing that, but the thing you shouldn't be doing, so we can't, so this is the thing, right? So we can't make side effects UB. That's one thing we could do. That's what C++20 contracts did. I think this is one of the reasons why it failed, because adding more UB to the language is bad, so we go out of our way to avoid that. But we also cannot enforce that an expression doesn't have side effects at compile time, because proving that something has a side effect is the halting problem. And if you reduce this to just the expressions where you can easily prove that it doesn't have a side effect, then you're basically restricting yourself to integer comparisons and not really that much else. So you want to be able to call, vector size in a contract predicate, right? But then you would have to prove that vector size has no side effects. We don't really know how to do this in general. I don't think it's actually possible. So we say that side effects are okay, and there are these cases where you might want to have side effects, but they're not going to affect the state of the program around it. And so you can do that, but you got to be careful with this. And if you follow this guidance, then you get a benefit, which is you can't get these Heisen bugs, where you have a bug, you add an assertion, the bug disappears. You disable the check, the bug is there again, right? So that is something that you can easily run into with macros, but not with P2100 contracts. The downside is, as I said, you can't just textually replace assert with contract assert. You need to be a little bit more careful with this. There are actually some tools that there's this other paper here, P3290, which proposes some facilities that make it easier to migrate away from macros. So that is also heading towards the appropriate study group in the committee. All right, so we talked about calling and returning from functions. So I want to drill into this a little bit more. So this is another diagram I borrowed from Lisa. Thank you, Lisa. So this is kind of what you want to do, right? We have a caller, you call a function, and then we check the preconditions, we execute the function, and then we check the postconditions, and then we return to the caller. This is what we want to do. Unfortunately, C++ doesn't work like this. C++ has translation units, so C++ works like this, right? So these things might be in different translation units. So the caller and the callee might actually see different sets of preconditions and postconditions. And in particular, you might compile the right translation unit with checks on or with checks off. But if you compile it with checks off, you might still want to enable the checks on this side, because you still want to do the checks, and you don't want to recompile that thing. Maybe you can't. Maybe you only have the binary without the checks. You still want to enable the checks, so you will be able to enable them caller side. But then it doesn't really depend on whether they're enabled callee side or not, and you should still be able to link these two things together without like any IBA break or anything like this. And the paper is specified in a way that lets you do that, but that has a consequence, which is you might get the checks twice. So if you have here on the left-hand side a caller and on the right-hand side a callee, and it just checks a precondition, and as long as it's a pure expression, everything's fine. But let's just factor this out in a different function. And then let's add a side effect to it. Let's just print like a trace we call this thing. And if you then compile and link that together, depending on like the settings and the different translation units, the output of that might be nothing if checks are disabled in both translation units, or it might be hello, or it might be hello, hello, or it might be like 5 times. We actually don't restrict the number here. So that means you can have side effects in your predicate, but you cannot rely on them happening. So it's very, very similar to copy elision, right? So if you have a copy construct that has a side effect, because of copy elision, you cannot rely on those side effects happening any particular amount of times, and it's pretty much the same thing here. That's something else to keep in mind. It's another reason to avoid side effects in contract predicates. But once we figured out that this is the right model for C++, we could solve another problem that all the other proposals from the last 20 years didn't know how to solve. It was a really, really hard problem, nobody had a good solution, and suddenly it was really obvious, which is how do you put pre and post on virtual functions? So Eiffel and and Ada solve this in a particular way, but then they don't have translation units in the way we do. They don't have multiple inheritance, and there's a bunch of other stuff that they don't have where kind of that is just kind of not applicable to C++. So how do we do it? And now it's really obvious. Well, the statically called function, the one you call, that's the caller side contract, and the function that is actually picked by virtual function dispatch. That is the caller side contract, the callee side contract. So if you call a virtual function, you're going to get these checks in this sequence. It's first going to check the precondition of the function you called, then it's going to check the preconditions of the function that actually has been chosen, like the final overrider, then it's going to execute that, it's going to check those postconditions, and then it's going to go back to the caller and check the postconditions of the function that you statically called. And so that solves a lot of problems, like the multiple inheritance problem. For example, if you have a unary function and you have a precondition that there must be one argument, and a binary function with a precondition that there must be two arguments. The thing that you could not do until now, but now you can, is you can inherit from both of them, even though they have conflicting preconditions. And that's fine. And it just depends on how you call the function, right? If you call this variadic function that can take any number of arguments through a reference to to itself, then there's no contract violation. If you call it through a reference to unary function, it's going to tell you that you have to have one argument because that's how you use this interface. If you call it through a reference to binary function, it's going to tell you need two arguments. If you call it to reference to variadic function, then you're good, right? So turns out that it's actually doing it this way captures exactly all the bugs that you want to catch. These preconditions, if those fail, that indicates that you called the interface incorrectly. Then if that one fires, it means that this function that got selected by a virtual function dispatch was not implemented correctly. And if either of those fire, it means that the function on the right-hand side isn't actually substitutable for the one on the left that you called, which means that you have a bug in your inheritance hierarchy somehow. So that is a very fascinating topic. There is a paper here that you can read, and there's also a talk by Lisa that goes into quite a lot more detail on this. I have 13 minutes left, so let me just quickly whiz through a few more things. So if you have a function with pre and post, and you have a pointer to it, you can call the function through that pointer, and the contract will still be checked. However, you cannot put the contract directly onto the pointer or onto a type def or something. There are very good reasons why this doesn't really work. You can read about that in those papers. Pre and post can refer to private variables, even though they're on the interface, and there's, you think about it for a little bit, turns out there are good reasons why you need that. And then referring to non-reference parameters in post. So you can have, for example, here clamp. Everybody knows what clamp is? Okay, good. So it has these preconditions and these postconditions. And very, very often you want to refer to the parameters that you passed in the postcondition. It turns out that in P900, if you want to do this, those parameters need to be declared const. So normally today in C++, this const on a value parameter doesn't mean anything really, but we require that if you want to use that in a postcondition, precondition doesn't matter, but postcondition, it has to be const, because if you would not require this, you could do this thing here. You could just modify the parameter and have some kind of dummy implementation that does something broken, and the postcondition would still succeed, because it's actually not talking about the parameters you passed in, but some other value that it doesn't even know that it has been modified because it doesn't see the body of the function. So we have to rely on the parameters not being modified inside the body, which is why we require this const, and we also require the const on any overloads of the function. So with P900, this is not going to compile until you put the const there. And there's another weirdness here with coroutines. If you have a coroutine, you put pre and post. Pre is fine. If you post on a coroutine, and then you use a parameter, it turns out that even if this is const, the way coroutines work is they will move out of a parameter, and they will create a copy of that parameter for this like coroutine frame thing, and they do that even if it's const. So if it's an integer, you don't really observe it, but if it's some kind of user-defined type, like a big integer, it turns out that the big int inside the body is actually going to be not the same as the big int that you passed in, and the big int that you passed in will be in a moved from state, even if it's const. This is very surprising and weird, so we make it ill-formed to reference a non-reference parameter in post if the function is a coroutine. And the last thing we have here is this thing called Constification, where, as I said, we don't really want you to modify state in a contract predicate unless you know what you're doing. So what we're doing is every variable inside a contract predicate is implicitly const, exactly in the same way that every member function is implicitly const if, every member of a class is implicitly const if the member function is a const member function, right? You can't modify any members, they're implicitly const. Same thing here, if you try to do this, compiler is going to tell you, well, those variables are implicitly const here. And that prevents a really, really, really common bug where people don't understand that you can turn assertions off and they put something meaningful in there, like process, do this thing inside the assertion and then make sure it's true, and then they are confused because you turn the checks off and then the process no longer happens. And so with Constification, this thing is going to be called, fail at compile time because process is not a const member function. The trade-off is if you have a function that doesn't actually do anything modifying, but it's just missing a const, then that's also not going to compile. So if you try this, so you have to actually add the const here. You have to be const correct, or if not, you have to escape it with a const cast, which works but is ugly. So here are basically all the cases in which we constify things. There's 2 exceptions. If you have a variable that is declared inside the contract, then you can modify that one because that one will never leave the cone of evaluation of the predicate. That will never be observable outside. And the other thing we don't do is we don't do deep const. We don't constify the thing that a pointer points to because you can't really do that. You can't do that for overloaded operator error because then you would have to somehow rewrite that implementation. You can't really do that. And then you can't do it for built-in operator arrow either because then it would be inconsistent and then raw pointers and smart pointers would behave differently and would be weird. So we don't constify things behind a pointer. That would be deep const, and we kind of thought about this for a while, and it turns out you can't really do that. Okay, so I got 10 minutes left, so I'm going to quickly talk about program correctness here, which is really at the core of what this facility is all about. So this, of course, is taking place in the context of safety. Safety is very important. We now are in a time where we need to make C++ more safe in order to have a continued a thriving language. There's lots of pressure from all sides to increase the safety of C++. And contracts are a very important piece of the puzzle here. But it's kind of interesting because it seems to be a little bit controversial. People talk past each other when the question comes up whether contracts are a safety feature. And there are people who say contracts are absolutely a safety feature and we must do this now. And there are people who say contracts are not a safety feature at all. And so the reason why this happens is because people talk past each other. The word safety actually means very different things to very different people. And on the one hand, there is this concept that I call language safety, which is basically undefined behavior or the lack of undefined behavior, and that is things like memory safety, thread safety, type and resource safety, all of the stuff that all of these people in these talks talk about. You want to have a language that reduce the amount of undefined behavior in the language. And contracts don't really do that because they don't change the semantics of the language, right? They don't change the rules of the language. They don't give you a flag where you can compile your code and magically it has less UB. No, you have to actually add the contract checks in it, right? But what it does is it does something for this other notion of safety, which is functional safety, which is, I think, what safety actually kind of means for most people, which is the product is not going to explode and harm anybody or damage anything, right? So there's other stuff here, like system safety, which is part of kind of this half. So I suggest we just stop talking about just unqualified safety because people just talk past each other all the time. And we say what we mean. We distinguish these things, right? Do we talk about the language rules or do we talk about functional safety? That's a very important distinction. And the third thing here is security, which is yet something different, which is can't be exploited by a conscious, malicious attacker that wants to break your product. So this is something that J.F. Bastian said in his talk about safety. I believe it was C++ Now 2022. A bunch of people have done talks about this, but this is a good quote. No functional safety without security and no security without type, resource, and memory safety. So I think that is a very good observation, and it gives us this kind of Venn diagram. So this is all C++ code, okay? And then there's a subset of it that has no undefined behavior. So I think practically, technically, this is probably very close to the empty set. But, but I'm not talking about like things that have undefined behavior for like academic reasons because the standard is weird, but I'm talking about undefined behavior that actually can have bad consequences, right? So there's some subset that doesn't have that, right? So then you eliminate, if you could hypothetically somehow do this, you would eliminate these like 70% of CVEs that people keep mentioning in the talk, so you would still have the other 30% left. So that doesn't guarantee that your code is going to be secure, but there's going to be some subset of that which is secure, right? And then there's going to be some subset of that which will be functionally safe, which is not going to explode and do bad stuff if something goes wrong. And then there's a subset within that which is actually correct code that actually does what you want it to do. And contracts help you to get more code into this green zone. That is what they do. And if you move more code into the green zone, and every contract assertion you add to your code is going to help you do that, then you get all of these other properties as well, right? So one last thing is, so this is kind of what contracts are about, but the other distinction to other features is that they don't do that by changing the language somehow. They don't change the semantics of the language, they just add checks, which are just expressions. So one thing that's important here is during program evaluation, right? So there are things like, Sean Baxter's Safe C++ proposal that adds basically a borrow checker, which changes the semantics of the language, which changes the object model. So we're not doing anything like this. What we're saying is, okay, there's a bunch of ideas how to increase safety in C++ at compile time, and this feature is for all the stuff that you cannot catch like this. Once you actually run your program, there's still going to be defects there. We're going to help you catch those by expressing what you expect your code to do everywhere, and then you can catch those things and hopefully make your code correct. Program evaluation does include constant evaluation. So if you have like a compile time function that you call while you're instantiating a template, and then that has a precondition on it, that will fire at compile time, and you will get a compiler error. But that's also still evaluation. We're just evaluating expressions. We're not changing the language semantics in any way, which means, for example, you can't do things like if you have a function that has no definition, you can't put that in a contract assertion because you're going to get a linker error because that's just an expression, right? And here's the last point I want to make. So there is this concept of a plain language contract, right? Which is the actual contract that your program or your function or your class has. This is the thing that you expect it to do in order for it to be correct. And if your program or your class or your function satisfies its plain language contract, it is correct. Now, turns out that we can't check every part of the actual plain language contract with contract assertions. For some of the things, it's very easy. If part of your contract is you don't call this out of bounds, you can just straightforwardly add an expression to check that. If the condition is slightly more complicated, for example, binary search has a precondition that the range is sorted, right? I think we all know this. The problem is if you can add a check, a contract check, but if you actually then perform that check, that is going to break another part of the plain language contract, which is that the function is O log n, because this check is On. So if you check that, you're going to break the complexity guarantees, which is another part of the plain language contract. So you probably don't want to do that check every time in every debug build, right? You want to maybe do this only in a special super debug build or something. And sometimes you just cannot insert a check for program evaluation that lets you check whether a part of the plain language contract has been satisfied. For example, pointer points to an existing object. This is the classic memory safety problem. To check this during program evaluation, you would have to do instrumentation like ASAN or something like this. To check it at compile time, you would have to either have no pointers or references or something very similar to a borrow checker. So you can't really do this with just a kind of a bool expression here. Or this function will return a value, or because that is solving the halting problem. Or I have been paid today, and if not, then I don't guarantee that this code works. This is another plain language contract which you cannot express in code. So that means that contract assertions can specify only predicates that can be checked. And that also means that contract assertion can specify only a subset of the actual contract. That's really, really, really important. So a correct program is a program that, when you evaluate it with whatever input, satisfies its plain language contract. Contract assertion will help you find some of these violations, hopefully a lot of them, but not all of them, which means that contract checks are great for identifying incorrect programs, but they cannot be used to prove that your program is correct. That is conceptually impossible, right? And so while the primary use case is checks during runtime, they can also provide useful information to a static analysis tool. Like static analysis tools use assertion macros today to derive information from them. That is helpful. You can find bugs like this. But they have to be in the body, so if the analysis tool doesn't see the body, then it can't derive any information. So pre and post make that better because they're on the declaration, they're not macros, they can't be textually removed and stuff like this. So they're great for a static analysis tool, but you can't use them to like formally prove that your code is really correct, some kind of formal verification. That's not really what this feature is for. So, okay, I'm done now, I'm out of time. The last slide is extensions that we foresee for the future that but don't have in the paper right now. There's a bunch of them. I'm not going to talk about that because I'm out of time. I'm just going to mention one. You want to add these post-condition captures, which let you express things about, well, the size was this before the function was called, but the post-condition is that it's now something else. So kind of remember the values at the time when the function was called and then check them later. So this is a feature that's not in the paper, so it's probably not going to be in CSS26. I don't think any of this will be in CSS26. That's just future extensions, which I hope you will get at some point because it's going to make the contract facility more usable. And that's all I have. Thank you very much.
Hey, Timur. So you said that the post conditions are checked like after the locals go away within the function. Mm-hmm. So if I like take a stack trace in my contract violation handler, or like if it has a breakpoint for a debugger, when I look at that stack trace or I'm in the debugger, am I going to have the stack frame with the function on the stack, or is it going to be gone by the time I'm in the post condition?
So you will actually have the violation handler on the stack.
Okay. So
what you have to do, and I had this on the slide, you have to actually take the stack -1. I don't know if I have time to go back to that example. But
it's all right.
Yeah.
Okay. And then my next question, can your contract violation handler do the termination itself? Like if you want to terminate in some way that is different from what the standard does? And is there a way to customize, like if I'm doing quick enforce, is there a way to like customize how the termination is done?
So we say that the termination mode is implementation defined. So for example, we would expect that in quick enforce, you just get a built-in trap on Clang, something very, very quick. And in enforce, regular enforce, you probably would call terminate or abort or something like this. So we don't really specify it, but you can also, if you want to have a guaranteed, so first of all, the compiler is going to document what's going to happen because that's what implementation defined means. But if you as the user need to call terminate because they need to rely on the termination handler being called, or you need to call abort because you have a SIG abort handler that you want to be called, you can just call abort or terminate in the violation handler. That's all fine. It's just a function, right? You can do whatever you want in there.
Last question, you mentioned that you can end up in a situation where the checks may be run redundantly, like both on the caller side and the callee side. Do we expect the compilers will be able to optimize that, at the very least through LTO?
Yes.
Okay, all right, cool.
So we are working, I should actually mention this, we are working with implementers. So this has all been implemented in Clang and GCC. You can play around with it. If you open the paper, P100, there's somewhere links to like Godbolt. You can play around with it today. Obviously, that doesn't let you do the compile different translation units and stuff. But there is a branch of Clang that you can play around with the stuff. So yes, we expect that that's going to work.
Okay, thank you. No time for other questions, so we go for lunch. Thanks again.
All right. Well, catch me during lunch and ask me more questions. Thank you.